Yeah, the recording will be sent out. So if you can't stay for everything, if you can't stay for all of STEMTober, it will be accessible later on. Okay, great. We are recording. So I am going to make Dr. Spang. Oh, Sophie, can you spotlight Dr. Spangler?
Yeah.
Okay. All right, welcome everyone. We're so excited to finally kick off STEMTober. STEMTober is hosted by Wave Learning Festival and STEMI. Wave Learning Festival is a nonprofit educational platform that offers free courses for middle and high school students by college students in an effort to improve educational equability. And STEMI is also a nonprofit organization that hosts STEM classes and events primarily for middle and high school students. For those of you just joining us, every Saturday in October, we'll be focusing on different STEM field for interested students who may not have had much exposure to STEM. And for our first weekend, we're all about engineering. Our second weekend will focus on computer science and math. Our third on medical science and healthcare. And our fourth will be on the natural sciences. So now, Sophie, please take it away with introducing our first speaker.
Hello, everybody. I hope everyone's having a great day. So welcome to Dr. Jamie Spangler, who is an assistant professor in biomedical engineering at Johns Hopkins University. Dr. Spangler earned a BS in biomedical engineering at Johns Hopkins and went on to conduct her PhD research in biological engineering at MIT. Today, we'll be learning more about her and her research. So to get on into the questions, there will also be a time where everybody could ask questions after I ask a bunch of questions. So yeah. I'm gonna start all the way from the beginning. So as a child or a teenager, did you wanna go into a STEM career?
Yeah, it's a great question. I've always really been fascinated by math and science. My father actually was or is still a math educator. And he did, in addition to teaching courses at a community college, he was a math textbook editor. He wrote math books, and everything was math. And I was actually sort of the playtest often for his math books. So he would come up with these different problems. And for me, it was always a mystery, right, to solve whatever problem would come up, and I couldn't go to sleep at night, before I would solve his problems and figure out, sort of crack the code. I was always very into, sort of solving it and uncovering these mysteries. And math and science seemed to be a way, right, that you could actually use quantitative analysis to sort of get to the bottom of things, right, to understand the world around you. And I became very interested in how we could use quantitative sciences to understand and potentially manipulate the biological world around us, right? The world of healthcare and medicine. And so I think it was sort of always as a child, there was kind of this background, pushing me toward math, science, and discovery. And then it was a little bit later, probably toward high school and then into college, where I became very involved in how we could apply this to medicine.
That's great. Like, I love how you have like a personal story connected to your discovery of like STEM in general. That's great. Like you said, like you got more interested and more involved in like high school and college. So what high school experiences have aided you like in your profession now and like in college in general that like were STEM related or just in general?
Yeah, I mean, I think I always tell people, in terms of the skills that are most important in your scientific career, sure, like, you obviously have to have a baseline understanding of, physics, chemistry, biology, right, to do all the different things you do. But I think like a lot of the life skills that you learn about sort of being patient and, sort of being patient, but not too patient, right? Being patient about the fact that, science will go at its own pace. You won't always necessarily have that answer right away, but that you should always be pushing, right? That you should always be persistent, that you should be resilient, and you should always be working toward a particular goal. And so I think that really a lot of what you learn, not just in the classroom, but also through your interactions, and also then in my experience, ultimately through actual laboratory experiences and research, I think are very instrumental in kind of building the skills that will ultimately make you successful in science. And I will say that although I had many experiences in the classroom, laboratory related, I did feel that it would have been really great if I had had opportunities in high school to actually conduct research in an academic lab. And when I got to college, I jumped right in and took advantage of that. And sometimes, I think for those of you who are worried, right, that, oh no, I didn't do research in high school, or I didn't do research in middle school, like I'm never going to make it. It's not true, right? You can start, it's never too late to start. You can start anytime. You can start anytime in your college career. You can start thereafter, right? And reinvent yourself. And so I would really encourage you to definitely follow what your passions and what your dreams are, but to take advantage of all opportunities, as early on as you can, to do what it is you love, and make sure that is what in fact you love, and what you want to do with your career.
That's great. Thank you so much. That answers like my third question also about.
Oh, sorry.
No, of course not.
Ahead of the game here.
It was about what advice you would give to like high school students and like college students, but you really like went over that, and that was a really good answer.
Yeah, no. I mean, just to follow up also, again, I would say in high school, again, don't worry. Definitely try to create opportunities and do things, but don't freak out that like if you don't participate in things, or you don't have those opportunities for whatever reason, that you'll be at some sort of disadvantage, because you're not. You always have that opportunity to start. And I'm constantly, every day, right? I'm jumping into new fields and reinventing myself in different ways. So don't worry about, sort of being behind the eight ball if you're not able to do it. But then again, on the other side, kind of like I answered, in the first question, is to really take the initiative and see what opportunities are out there, because that's the only way you're going to find out, what's right for you and what's the best path.
Right. I feel like that's a very good message, especially to our seniors, because everyone's like, oh, we have to do as much as we can to get involved. But yeah, it's really about patience, and I agree. Like that. Thank you so much for that.
Mm-hmm.
Moving on to like a little bit about Johns Hopkins University, like what's like your favorite part about working there, and like can you describe a little bit more about the community also, and just like about like your teaching in general?
Absolutely. You can probably see right now, this is my beautiful office at the Smith building, which is right in the heart of the medical campus. And I guess that says it all, right? Being right in the heart of not just any medical campus, right? But the premier medical institution, not just in the US, but in the world, right? And I'm constantly engaged and exposed to people who spend their lives, right, curing diseases that are impossible to cure, making medical discoveries that are the future of science and medicine. And the fact that I can bring my engineering tools, right, and integrate my sort of analytical quantitative approaches with the forefront, right, cutting edge of medicine, is just everything for me. And I just can't imagine myself, being anywhere else, because ultimately, if what I want to do, right, is apply my engineering background to translational medicine, this is the place to be. This is ground zero. And so I think that that's been, a huge draw. Another wonderful thing that I really love about Johns Hopkins, and this is, I think, more luck than anything else, because I think that, the outstanding resources, facilities, expertise, and people here, that is amazing in and of itself. But what's even more amazing to me is how incredible my colleagues are, the people, not just the faculty, the students, everyone around us, the administration, the staff members, everyone here it's just such an incredible environment and community, and everyone is just so passionate about the science, about the research, about what they do, and about moving things forward. And I think that's, like I said, part of it is luck, right? But part of it is we're all here because we have that shared common vision and that same mission. And I think it's just a very unifying factor for all of us. And it's just really, again, kind of an incredible experience every day to not only enjoy and love what I'm doing, but to see what's going on around me and to be so excited and engaged and stimulated by it.
Yeah, that's great. You mentioned in like your answer, like how you could apply your engineering skills into the medicine and biology world. When you did go into biomedical engineering and bioengineering, like, were you interested in biology or engineering first? Like, what came first for you?
Yeah, it's a good question. I think so. They kind of, I guess, both sort of came together because, as I mentioned, I was always into science and math, but in my sort of pre-college curriculum, there wasn't really engineering, right? That wasn't really a thing. There were opportunities, right? You had physics class, and you had chemistry class, and you had various exposures to various elements. But there wasn't really an engineering class, at least that I had an opportunity to take pre-college. And so I would say that a lot of my exposure really to more advanced biology and engineering came through my collegiate major. Again, I had high school biology class and all of those things. But I think that really where it all started connecting and coming together was probably in my college major. And what was really nice being in the biomedical engineering program at Hopkins is that it's a very integrated curriculum. It's not, you take your bio class, you take your engineering class and figure it out, put it together in your head, right? This is an integrated curriculum where every class that you're taking is part of the biomedical engineering major, right? And dedicated major. And everything, sort of is put together and synthesized in a way that really makes sense to you. And, everyone learns differently and everyone sort of has a different style. I'm the person, I kind of like all of it at once, right? I like getting from a lot of different directions and sort of having a lot of different things ongoing. Some people like to sort of focus more on kind of one thing at a time. And the biomedical engineering major in the biomedical engineering world, I would say, works for all learning styles and all types. I think it really just depends, sort of what you want and what your vision is for your academic trajectory.
Right, that's great that you feel like that there's room for wiggle room, at least for like having different types of learning and like different types of how people like approach things in that sense. A little bit. Okay, so in STEM world, I don't know if everyone here has attended STEM world, but you talked about your research with the engineering of proteins for protein therapeutics. And can you give like a little, you don't have to go into full detail, of course, but
I'm always happy to blab on and on for ages about the awesome research going on in my lab, but I don't want to belabor or bore you guys. I know this is more, high level. But yeah, sorry, finish your question.
Yeah, of course. Just like you could give at least like a summary of it. You could go on for as long as you want about it because it's so interesting. So I'd rather hear about it. But yeah.
No, sure. So again, at a very high level, so over here, actually, you can probably see I have my protein friends. And I don't have a lot of real friends in real life. No, I'm just kidding. But these proteins keep me company during the long days when I'm sitting in my office doing work. And I think, it also keeps me grounded and foundationally, sort of is the building block of all of life, right? Of all of biology. Everything is based on proteins and ultimately the amino acids, right, that make those up, and the nucleotides, right, the DNA that encodes those proteins. And so what my lab is very excited about doing is taking proteins that exist in nature and reshaping them, right? Making mutations to them or making some sort of changes or modifications, or inspired by natural proteins, building entirely new ones that nature's never even seen before that could be useful for therapeutic purposes. So what types of therapeutics, right? So you can imagine some types of therapeutics you might want to block, right? A certain protein-protein interaction or a certain signaling pathway or a certain event. So that would be called an antagonist, right? So basically just antagonizing or preventing a particular event from happening. Other drugs are what are called agonists, meaning that you actually activate or stimulate pathways that might be good for healing. So one example would be if you think about the immune system, and we do a lot of engineering of immune proteins, both for antagonism and agonism, and both to activate the immune response and to suppress it. So you think about what's going on right now, right? COVID-19, you might want to activate the immune response, right? To kill pathogens and destroy the virus as it invades. But actually the reason that people die ultimately from COVID-19 is because of an hyper-inflammatory situation called cytokine storm that leads to an overactive immune response that ultimately will kill you due to various organ damage and other sorts of downstream events. And so what our lab is trying to do is think about different ways, right, that we can manage the good inflammation, right, the good inflammatory response where we actually kill and destroy things that are invading, or for example, cancer, and balance that, right, with having, you know, an over-inflammatory response or some sort of autoimmune response, potentially against our own, you know, self-antigens, and try to create therapeutics that will, in a targeted and sort of clever way, be able to navigate that space and keep people healthy.
That's a great way to describe it all, especially because I feel as people will learn like about proteins in like class, and they won't be able to relate it directly to like something that's in the real world, and having that experience and having your story with what you do in the lab is really important to show everyone, in my opinion. So that's great. Thank you for
Thanks.
sharing.
Yeah, no, like I said, and you know, I mean, the fact that I'm talking about COVID-19 is not coincidental. We do actually are actively doing research in that area, really trying to understand the antibody response to COVID-19 exposure and how that may play into the ultimate outcome for patients who are diagnosed with SARS-CoV-2.
Wow, that's impressive that you guys are even on top of that, like as it's going on. That's crazy, but yeah, that's great. Okay, so this is a little off topic from Johns Hopkins University, but you studied at MIT for your PhD in biological engineering. Like, how would you describe your experience at MIT, like other than like Johns Hopkins University?
Yeah, it's a great question. I've been a few different places because I was an undergraduate all the way back in the day, because I'm old, back here when I was in undergrad at Johns Hopkins as an undergraduate. And then I did my PhD, as you mentioned, at MIT up in Boston. And then I did my postdoc all the way on the other side of the country in Stanford. And then I actually grew up in Chicago, and I'm back here. So I've lived, you know, sort of all over the map. At least all over the US map. Yeah, it was an interesting experience. So what's interesting too about MIT, and something I'll say about that institution as well, is again, and I think this is maybe a generalization in science, but people are just so passionate about what they do, so excited about their research, but also so humble, right? There's this level of humility. And I think it's part of being a scientist, because I'm also the same way. It's like, there's a lot of things that you know, because you've been trained for a long time and you've experienced that, but there's so many things that you don't know, right? And that you're constantly learning and you're constantly being exposed to, and that nobody knows, right? That we just don't understand. And again, I think that just being immersed in a place where you're surrounded by others who also share that excitement for discovey and for uncovering mysteries, is just such a cool place to be. So MIT, yeah, again, you just feel like you're surrounded by, such giants and such greatness, but also everyone's just so humble, and everyone's just so down to earth about, I think we're all just humbled by science and by nature and by, everything that's out there that we don't really understand.
Right. That's a great way to describe it, about like the commonality of not like knowing the unknown. So that's a great way to like describe it. And I was also going to ask about Stanford University, regarding the research that you did there. Like, can you explain a little bit more about that with the cytokine system, right?
Absolutely. So yeah, we were, that was a real foray into cytokine engineering. And we were very interested. We worked for Chris Garcia, who's faculty jointly between the molecular and cellular physiology and structural biology departments there at Stanford, at the School of Medicine. And what drives him is really protein structures and interactions. And he is a preeminent crystallographer and protein engineer. And my interest in his lab was primarily focused on the cytokine interleukin-2 or IL-2. And I explored this cytokine in a number of different contexts, both, as I was describing before, trying to make mutations on the cytokine and engineer its behavior to target it toward different types of immune cells, for modulating the immune response and tuning that. I also was more generally interested in ways that we could design sort of these new cytokines that nature's actually never seen before, that we called neokines. And we partnered up with David Baker's lab at University of Washington, who does a lot of computational design. And we were working with them to actually de novo build these cytokines that mimic the behavior of naturally existing cytokines, but do it better, right? They're more stable, they're more targeted, they're more selective, and they're more therapeutically useful. And so that was sort of another angle. We also had a few other angles where we were trying to design cytokines, and in some cases antibodies, that would alter the interactions between membrane-bound receptors. So receptors are, as the name would suggest, receiving the signal coming from soluble cytokines and transmitting that into cells. But the actual way that they do that is through interacting with each other, and then their intracellular domains inside the cell bumping into each other and activating downstream pathways. And so we were trying to understand what power we had to actually manipulate the interactions going on between the membrane-bound receptors so that we could create entirely new signals by just modulating the actual cytokine or soluble molecule that was bringing the receptors together.
This is more of a broad question, but to give the audience a little bit more about like how you actually work on proteins, like what is the process like of working with like cytokines and like proteins in general? Like how do you like actually like do it and focus in on it?
Yes, I know all this has been sort of in the abstract. Look, we can engineer proteins. So what does that mean? I always tell people, if you want to engineer proteins, you have to know how to make them. So we do a lot of biochemistry, and that involves basically encoding, well, ultimately molecular biology, where you have the DNA sequence that encodes a particular protein, and then you just dump that in to a cellular system, whether it be bacterial or yeast or mammalian cells, and then you tell the cells, right, based on that encoded DNA plasmid, to make your protein, right, to express your protein. And then a lot of what I tell people that our job is actually purification, right, purifying the good from the bad, right, separating the good stuff from what you don't want. And so we actually extract the protein from the whole milieu of what comes out of these different cell systems. And then we have our pure protein to do whatever functional assays, whether they be signaling assays, whether they be treating, cells and looking at their molecular trafficking, whether they be treating our own cells, right? Taking our own blood and looking at, how our own cells respond to various perturbations and proteins that we engineer, or whether that's putting that into an animal, say a mouse model or rat model, or even a larger animal model, non-human primate model, or ultimately developing a protein in exactly the way that I described, using what's called GMP or good manufacturing practices, so that you could put it into a person for a clinical trial.
That's a great way to describe it, and just like give people more insight on that. I love that. This is more of a very broad question, but who has been one of, or we'll say it in general, like which people have been the most influential people in your life and why?
Yeah, so I was gonna say it's always like hard to pinpoint, exactly one person and like who's sort of your go-to, whatever. I mean, from early on, it was definitely my parents. I mentioned that my father is a math educator, and when other people probably were playing video games, I was sitting around, like staying up till all hours doing math problems and writing those out. And that was just something that, a common bond that I shared with my dad very early on. And I think that really shaped a lot of, what I went on to. And both of my parents really just had a very strong work ethic for what they did. And I think that really, again, passed down the nature versus nurture question, to me, and really motivated me to pursue my own dreams and ambitions. Later on, I would say that one of the most influential people for me was my undergraduate research advisor, Kalina Rostova, who's actually here at Hopkins and is now a full professor, and is coincidentally one of my academic mentors. As I'm, obviously, one of the important things that I would stress to all of you is to find mentors, identify mentors early on, and to use them, right? Don't expect people to come to you and be like, hey, can I be your mentor, right? Find people that fill that mentorship role for you and engage them and persistently engage them. Almost 100% of the time, or I would say 100% of the time, people will be willing to and they will want to, but they're busy, right? They won't think of it organically, but if you ask them, everyone will be willing to help you. So Kalina was just instrumental for me because it was my first exposure to research, because I hadn't done anything pre-college in terms of laboratory research. And just seeing the excitement on her face, right? When we would run a gel, or when, we would purify a plasmid, or whatever we would do, right? That passion and that excitement just lit a spark in me. I already was very excited about like research, but when I saw that this was something that you could actually do as a lifelong career, and not only do, but also inspire others, right? That I myself could not only, be a part of the research, but actually inspire other people to pursue their own passions and pursue their own research, was just amazing to me, because I didn't even know like that was an option, right? It sort of just seemed like, okay, you're into medicine, so go, be a physician, or, okay, you're into engineering, so go work for a car company, like that sort of thing. But I think that the opportunity that this was something that I could actually do in a research career, I think really, really excited me. So, yeah. After that, and this is going to sound probably cliche since they were, obviously the most influential people in my science career, was of course my PhD supervisor, Dean Wittrup at MIT, who is an absolute giant, who literally gave birth to, the protein engineering in a way through his development of the yeast surface display platform. So there were other display platforms that people use for directed evolution, which won the Nobel Prize a couple of years ago. This process by which you can actually mimic Darwin in a test tube. And what Dane did was he brought directed evolution to the masses by creating this technology known as yeast display that's sort of an intermediate between phage display, which is sort of much simpler but also much dirtier, and mammalian display, which is more sophisticated but also is not very tractable and has a lot more sort of caveats about kind of doing it right. So phage or yeast was sort of the nice balance in between. And that's an incredible technology that has just taken off and created an entire field. And what's so inspirational to me about Dane is that he literally created this entire field, right? It's not just that he was training the people in his lab or, having the influence, directly, but he's also indirectly, right, having this huge legacy of an entire field of science and field of investigation that no one could have ever anticipated, with his discovery. So he's a huge, inspiration to me. And then Chris Garcia, my postdoc advisor, is just absolutely, I would say, hands down, the most brilliant person that I know. The level of creativity and sort of his insight and cunning that he has when he looks at problems and specifically at biochemical and biomolecular interactions is just staggering. And it was just an amazing experience to work in his lab and to have access to him and to have access to the resources and all of the expertise and opportunities that were there at Stanford. So I would say, yeah, it's been shaped by a number of different people depending on the different stage of my life. But it's a great question. I would really encourage all of you to utilize and to proactively engage mentors.
That's great. Yeah, like even how you have people that influence you all the way from the beginning and just like showing their passion and how everybody that you mentioned has like a certain passion and a drive. And especially like how your advisors in general and your mentors, like you mentioned how like people should go and get what they want and like ask and like reach out. And I feel like that's also really important and a central theme that like you've been mentioning about passion and just like going after your goals but being patient at the same time. So that's great.
Yeah, it's an interesting point too. And I guess if nothing else out of this interview, I hope that it'll come through that like there's a very delicate balance, I think, between going after your goals, right, and being persistent about it, but also waiting for things, sort of being patient for them and having understanding and acceptance that you're not always going to get, the results overnight, that things do take time and effort and persistence. But I think that there's an important sort of balance there to keep in mind, whatever career and whatever path you take.
Yeah, that's great. I agree completely. This is well, we've actually already asked this about the biology and the engineering. You said it was kind of like a mix, so that's good. One other question that I was wondering in general is what advice would you give to yourself if you were looking back into yourself and like say you saw your younger self, you know what I mean? But what advice would you give to yourself for the future?
Yeah, it's a great point. And I think the answer to that, right, depends on, where I'm intervening, right, where I'm talking to my younger self. But I would say that there's a constant theme, no matter where in my life, I'm intervening with my time machine. I should always be telling myself to not doubt, right, my own skills and ability and talents. I think that throughout our lives, because especially in the academic world, we're exposed to so many people who are geniuses, who are brilliant, and there's always going to be someone who's smarter and better and faster and whatnot, than you are. But one of my favorite sayings, right, is you may not be the smartest person or the strongest person in the room, but you can always be the toughest, right? You can always be the most persistent and the most resilient and, sort of mind over matter, keep pushing, toward your goals. And so I think that there can be a lot of issues with, sort of losing confidence in yourself, or just, being intimidated by situations that you get into. I can think of a number of different points in my career where I was just like, all right, this is it. I'm not going to get into grad school. I'm not going to get into any of these postdoc labs. I'm not going to get an academic faculty position. It's too hard. I'll do my best, but it's not going to work. And I think as much as you can, rid yourself of that attitude. Don't let that dictate what you're going to do. Always go for it, right? Just put yourself out there. Let them decide, right? Let the department decide if you're, a fit for them, or if you're appropriate for a faculty position. Let the school decide whether you're, qualified to go there for grad school. Let your postdoc supervisor decide if you meet the bar for somebody who can be a postdoc in their lab. Don't ever, be the one to count yourself out, because you will lose 100% of, the times that you don't try. So I would say, and not that I always tried, I always, did that, but just don't let the sort of lack of confidence or negativity or other things deter you or stress you out or frustrate you in any way, because you will end up where you belong. I'm a firm believer in that. And also you will be rewarded for your hard work and resilience.
I feel like that's a great way to word it, especially because everyone needs that boost and like that reassurance that it's going to be okay at the end, obviously, and that hard work does lead you somewhere, and it's good to hear that from like someone as successful as yourself to say that.
I appreciate
it. Now we're going to take some questions from the chat. Diana, do you want to read some of them out, or do you want me to? You got it.
Yeah, I've been tracking all your questions, so we can start with the first one. Someone asks, if I'm looking to go for a physics major, will doing biology research be a setback?
There are no setbacks in life. I sort of always had this in the back of my mind, but I really, really learned it very strongly through my postdoctoral research, and with a lot of encouragement and help from my supervisor there. I think a lot of people think that if something doesn't lead to an immediate tangible outcome, that it's some sort of failure or it's worthless or all of these other things. And it's just not true. Life is not a linear path, right? Life has many twists and turns and situations. There are things that I did in my postdoc that like 6 years later, I'm like, that was so useful, right? For something completely unrelated that I'm working on right now. Or, that course or that, instructor that I had, or that particular project that I worked on is really coming in handy for something, that I never would have envisioned myself working on in my career. And so I guess my biggest point there would be nothing is a waste of time or of effort or of utility. And if you are very interested in physics, but also in applying that to biology, I would recommend taking more classes related to biology so that you have the background and the skills to be successful, in both of those fields. And for your research, especially, again, at the undergraduate or even high school level, I'm not sure exactly where you're at, keep an open mind, try different things and learn what it is you like and what you don't like, especially for a PhD. It's a long-term commitment to a particular thing. And if it's something that you're not so sure that you like, it could become problematic, because if you're not, passionate about it, it's going to show consciously or subconsciously in your ultimate work and commitment and productivity. So yeah, I mean, especially, early on, explore different things. Nothing will be a setback. Nothing will be a waste of time or a waste of usage of your skills. Every experience, you're going to learn something, and it's going to make you a bit stronger as a candidate toward what you ultimately want to do for your career.
That's definitely a great answer. If the person who asked that has any follow-ups, like, feel free to send them. This question is more less abstract. So someone asks if your research is more in silico or in vivo.
Okay, great question. My research, so actually in silico and in vivo are not necessarily the only options or opposites, I would say, because there's many things that could be done in between those areas. So my research actually spans from in silico to in vivo, because we create, right, and computationally design various proteins that ultimately will go into animals and into people eventually, hopefully. And so I would say that, and then in between that, we test them on cells or signaling assays or other various functional characterizations. And so I would say that my lab, because we're not directly the ones doing the computational work, I wouldn't characterize us as in silico, because we usually do that through collaborations. And collaborations, I'd just like to stress, and I mean, again, you guys are early on in your careers, but to really value the fact that everyone has some expertise and bandwidth, but it's limited, right? You can't do everything. There's only 24 hours in a day, and you're only one person. And so it's really, really useful to leverage the people around you, right, and the skills that they have to help you meet your objectives and meet your goals. And so we've had fantastic collaborations with David Baker's lab at University of Washington, and actually right here at Johns Hopkins in the Chemical and Biomolecular Engineering Department with Jeff Gray's lab, that have just been instrumental to figuring out the molecules that we want to create. In terms of in vivo, we have a lot of exciting animal model studies going on with various compounds that we've created, but I see those as a tool, right? It's not that we're an in vivo lab. It's not that we're dedicated to only doing research in mice. We use the mice to ask important biological and engineering questions, and then we use that information to inform the design process. And so the in vivo aspect of our research is sort of a tool for what we do, but I would say our bread and butter really lies in the design and the engineering and the discovery.
Sorry, I was muted. Yeah, that's a great answer. If the person who asked that, Arun, if you have any more follow-ups for that specific question, feel free to ask. And for, I'm just going in chronological order. So someone also asked if you have done work with like prosthetics or stem cells.
Okay, so prosthetics, not yet. But I never say never. We are always open to, this collaboration. There's phenomenal people actually in the department here who do biomechanics, who do prosthetics, and not just in the biomedical engineering department, but also in the mechanical engineering department, who do incredible research in that area. And hopefully someday we will have a collaboration. We just started, as of last year, our first collaboration foray into stem cells. So my lab is actually located in a center that is dedicated to immunoengineering, which is what my lab does, but also to regenerative medicine. And so because of being in the center and integrating with people in that field, we have become very intimately involved with collaborations involving tissue regeneration. This specific collaboration is with Warren Grayson, who's a phenomenal bone tissue engineer in the biomedical engineering department at Johns Hopkins. And his lab is interested in using various stem cells and progenitor cells to ultimately differentiate into bone tissue, or in some cases into cardiac or muscle tissue, to ultimately rebuild either damaged or injured, or in some other cases wounded or even missing sort of tissue. And so not a lot of people know this. I think everyone knows that the most commonly transplanted tissue is blood, but the second most is actually bone. And so there's a lot of demand for bone grafting procedures, both for traumatic injury or congenital bone disorders or deformations, but also, just for bone diseases, osteoporosis, right, which is like 50% of women are facing. And so there's a lot of need for, regenerative therapies in the case of bone. And what we're doing with him is trying to design a protein that will specifically stimulate fat cells, so actually adipose derived stem cells, to differentiate into bone, so that we could theoretically use that. And what we're actually using is discarded liposuction tissue from patient procedures, from donors who are just people undergoing a routine liposuction procedure, and seeing if we can actually use their discarded fat cells to turn that into bone grafts that could potentially regenerate osteogenic, or undergo osteogenic transformation and regenerate bone tissue.
Awesome, thanks so much. For another one, let's see. Someone else asks, what chem suits do you use? And have you used any compounds for chem suits? Erin?
I didn't see the question.
Oh, some people were private chatting.
Oh.
Chem suites. Yeah, what chem suites do you use? And have you used any compounds for the inhibition of protein expression?
So I'm not sure about the first part of the question, what they're asking, chem suites. Yeah, maybe they could clarify the question, or maybe I'm just not familiar with the particular software technology they're referring to. So to the second part of the question, you said they were also asking if we look at protein expression inhibitors. That's an interesting point. A lot of times when we're expressing and purifying proteins in order to make them, we want to actually increase, right, the amount of protein that we're expressing. And to that end, we've actually collaborated very extensively with my colleague here in the Translational Tissue Engineering Center, Jordan Green, who does a lot of polymer drug delivery and gene delivery. And so we're actually trying to use some of the polymers that he's created to enhance protein expression so that we can get larger amounts of protein out of our cells. In terms of inhibition of protein expression, a lot of times we're looking to actually inhibit the proteins themselves. So once the proteins they're already there, but can we actually block them from doing what they're going to do, right? Doing their evil function. But yeah, at the gene level, there's a whole field, an exciting field that we interact with a lot of synthetic biology, where people are trying to impact, right, at the DNA level, the transcription and translation of the proteins as well.
Arun, you can,
Oh no, the question is the whole chem suites thing was for like the computational part. because they use a range of softwares, and so I was just going to ask like what type of softwares do you use, because I know there are a lot of paid ones and then there are a lot of open source ones that researchers use, and the paid ones can do a lot of things like molecular dynamics and all these things and do a lot of the simulation work that open source can't do. So I was just going to ask like which ones do you use, or which ones do
Okay,
you
no, thanks for clarifying. Yeah, as I mentioned, so we're actually not computational people. We
Yeah.
collaborate with a lot of people who do. Typically because we collaborate with David Baker, who created the Rosetta software suite. Most of our work is done through Rosetta or Rosetta Doc. So I would recommend those. Those are all open source.
Yeah. Okay. Thank you.
Mm-hmm. They're not easy to use necessarily. You need, sort of probably a little bit of a boost, in first learning how to familiarize yourself. But there's a lot of tutorials online, and there's Refold It, or maybe it's called Fold It, I forget. But there's a lot of, sort of accessible softwares within that.
Yeah, because we found at the lab I work at, we found limitations on the software we use. So we were trying to find a better version.
What software were you using?
We were using a range. So we started for like the actual optimization, we used Orca, and then we used Chimera X to just visualize stuff. And then to do the topology for the proteins we were using, we used GROMACS.
Okay.
But GROMACS couldn't take in certain file types, and so we had to do it by hand, and we had to like map the protein itself, and so that was like kind of a pain. But we were trying to find, because I remember one of my mentors stated that they use different, like LSU, they use this whole chem suite that does it very well, because well, obviously it's paid, but it's really expensive apparently. So we were trying to find better alternates to it, or alternates to what we were using.
Yeah, I mean, if you have sort of the baseline knowledge and background of, how to use it, I think Rosetta is probably, gold standard for protein design. But yeah, for some of the docking or molecular dynamics simulations and other things, there are other softwares that might be more amenable to those.
Yeah, thank you.
Okay, one of the ones that I wanted to get to from the chat also, did you encounter any challenges as a woman pursuing a STEM career? Asks Beth.
Yeah, thanks, Beth. Great question. It's interesting, and I was talking with another one of my fantastic mentors is Jennifer Cochran, who is the chair of the bioengineering department at Stanford. She is my idol in every way, shape, and form. I have not become her in any way, but she's my absolute idol. She's amazing. And she told me this interesting story about, sort of her own experience, and it sort of resonated with me because I had a similar experience. So I grew up, I had two brothers, one older and one younger, and I was like the only girl, right, in the family. And so a lot of my experiences were sort of shaped by, being the only girl, right, sort of with other guys. And so I think that for me, it was never something that stood out, to me as like, even if I was the only girl in my program or my class or my major, whatever, like, and that was not the case, in terms of my major and stuff like that. But there were many times, yeah, where I would be the only female, in a particular class or in a group or in other situations. And I just sort of, I guess, kind of, it was normalized for me. And I think, again, a lot of that was I just grew up with brothers and I wasn't used to there being, other women around, frequently. I remember when I was in grade school, one of my friends had a sister and she was talking about how they used to like share clothes, from each other's closets. And like, that was like a foreign concept. I was like, wait, you share clothes? Like you like grab, like what? Like I have my closet, like no one would ever touch what's in my closet, right? It was just like a totally foreign, I would never touch anything in like my brother's closet, like whatever. So, it was just one of those situations where it became very much the norm for me. So I was just sort of used to it. So I never really paid much attention. So I would say that I think, it's wonderful that the field has progressed to this point, because it was not always like this, like it is now, in terms of, you know, being more open and welcoming to people from all different backgrounds and all different, you know, sort of ways, shapes, and forms. I think that there have been incredible pioneers for women in science who have paved the way and paved the path so that I can actually see things as, okay, you know, yes, I might be the only girl in the room or the only, you know, female like here, but I still am viewed and respected in the same way as my male colleagues. And it's just a non-issue. Like, it's just, okay, that's, you know, what your particular gender assignment is, but it's not, you know, preconceiving, I think, ways that people are going to view you or that you view other people. And I think that the more, you know, this conversation exists, the more that people are comfortable talking about it, and the more that, you know, it's just out there in the open, the more familiar and the more accustomed and ultimately comfortable everyone's going to become with it.
Yeah, it's great to hear that that didn't impact your research experience. This is, yeah, so this question is, can students still work in biomedical engineering if they dislike math?
Ooh, interesting question. So I like that you use the word dislike, because it's similar to my mom when I was growing up. Like, when I hated something, I hate this, I hate this. No, you don't hate it. You're just not so crazy about it, right? You know, like, she's always, you know, like, would put some sort of little spin onto, you know, different things. But I think it's nice that you use the word dislike instead of hate. Hate is a strong word. Dislike is also kind of a strong word. And I think that you know, depending, I'm not sure where you are in terms of being in middle school, high school, college, you know, where you are in your career. But I wouldn't worry about your tastes, you know, sort of at different points, because those can change. It's possible that, you know, your experience with math has been shaped by particular classes or teachers or concepts that you were learning that you just didn't like, that didn't resonate with you for some reason. But there could be other situations or other courses that you could take later on that you actually might end up loving, right? That you might end up transforming and turning around your impression of math. And so I wouldn't necessarily, you know, count that out. In terms of biomedical engineering, yes, there's going to be a lot of math, right? There's sort of a baseline understanding and background and knowledge that you will have to use in your career. But if it's something that you really, really want to become a biomedical engineer and to, you know, which is a very broad thing, it can mean a lot of different things. You can do something, you know, very, very much more in the biosphere. You can do something very, very much more in the engineering sphere. And so I think that there's a wide net, and you can definitely fall into that. And I wouldn't count yourself out, you know, like I was saying before, or count anything else out until you give it a chance and give it a fair chance and decide what you really like. And again, from the dislike standpoint, I think it's good that you've identified things that you just, you know, aren't really that excited about, because don't do anything. I tell everybody in my lab, and they always laugh at me because they're like the hardest working and most dedicated like bunch in the world. But I tell them, if you don't want to be here, if you don't wake up every day and say, I love where I'm at, I love the Spangler lab, I love protein engineering, don't be here, right? Like, I'm not going to take it personally. I'm not going to be offended. I want you to figure out what it is that you want to do, what it is that you want to be when you grow up, what it is that you like. Now, my graduate students, they're, you know, obviously, you know, at a stage where they've had a chance to figure out more what they want to do. But I've definitely had many situations with undergrads who come in and go, you know what, I actually really would rather code in front of a computer all day. Or I had, you know, somebody asked about the prosthetics. I had somebody who decided they were in a master's program and they just left entirely and went and worked for a prosthetics company. That's okay. If honestly, for me, that's a success. If I've helped somebody to identify what it is that they want to do or don't want to do, then I've helped them, right? I've helped them get further toward their goal. And that's a-okay with me. There are plenty of people who are very, very excited to do protein engineering and who are in my lab and do great things. And I'm perfectly fine, you know, if there are some people that come in thinking that they want to do that and discover that they actually want to do something else. It's a good question.
Awesome, thank you so much. I think we have a 15-minute break right now, but I know we didn't get to all of our questions. They are still mostly in the chat. I think a few of them PM'd me. Dr. Spangler, if you would like to keep answering them,
yeah,
definitely.
I can check. So where did we leave off? Can you tell me whose question?
Yeah, let me find it. Sorry, the chat just filled.
PINU.
Oh,
I see
yeah.
PINU as something about genetic differences. Yeah,
yeah.
I can respond in the chat here.
Yeah, so then from then. And then also I know a few were private questions. So if you did that, you can also just re-enter them in the public chat so Dr. Spangler can see. Or of course, yeah, PM Dr. Spangler. Yeah, so just to clarify, so right now for the next 15 minutes, we have a small break. And so you're welcome to, you know, take the time to relax. I think we can also just verbally communicate right now, so you don't have to, if you don't want to type out your answers, you can also just verbalize them. So
just do them. Okay, yeah, no,
oh, yeah.
I
Sorry,
think it's so much
that
easier
was
for me
not
to talk than right now. Okay, so yeah, the question was about heterogeneity, and great question. Heterogeneity is the bane of all of our existences, but that's what makes the world interesting, right? Is that we're all different. And so there's no good answer to how you solve that problem. And so our approach is to just try a bunch of different models with a bunch of different people and donors in the case where we're using human cells, and to look at how reproducible our results are across these different people and different models. But yeah, fantastic question. And then Pin, you asked another question about research on cancer and inflammation. So we do a lot of both. For cancer, our latest and greatest is sort of some molecules that we're using to generally stimulate the immune response that could be used as cancer therapeutics, and then also a new bispecific antibody that we've developed that specifically targets cancer metastasis. So interestingly, 90% of people who die from cancer actually die as a result of metastasis, not from the primary tumor burden. And so if you want to come up with a cure for cancer or an effective drug for cancer, targeting the metastatic pathways is actually a very promising route, and we've developed an antibody that does just that. So that's another area there. Inflammation. We don't do a lot of research per se on asthma, airway, inflammation type area. We do a lot of research on autoimmune diseases, which are also inflammatory in many ways, shapes, and forms. But our research in those areas is generally looking at trying to activate these cells of the immune system known as regulatory T cells, who are sort of the police people who kind of keep the effector T cells and other inflammatory cells in check. to prevent those from actually attacking our own healthy organs and tissue. And many of you, I'm sure, are familiar with autoimmune diseases, and unfortunately, I'm sure many of you know people who suffer from them. And so we've been doing research in MS, in diabetes, in Crohn's disease and colitis, and also in transplantation medicine to that end. Great. What was my motivation for getting a PhD? So after finishing undergraduate and my undergraduate career and being absolutely inspired by Kalina Rostova, who was my mentor, I knew right then and there, and again, you don't have to go, according to the same path as me, and many people don't realize, till much later on what they want to do and what they want to be. I knew I wanted to be a professor, and that was, the career path that I wanted to pursue. And obviously the ticket there was to do a PhD, and, I figured, let's start with grad school. Let's, just stay the course and, see where things go. But it's, the decision for me was sort of made itself once I decided that I wanted to go the faculty route. But for many people, regardless of what you want to do, the PhD is very enabling, whether it be a career in industry, in government research, and, again, consulting, any number of things. The PhD is just so powerful because it means that you've dedicated, right, a period of your life to answering and becoming the world's leading expert on a particular scientific problem. What's the difference between biotechnology, biomedical science, and biomedical engineering? Interesting and broad question, and I'm glad that you didn't ask the difference between bioengineering and biomedical engineering, or biological engineering and bioengineering. A lot of universities just call it different things, but honestly, what it means is shaped by the people that are in that department, right? And the research that goes on there. So if you have a program that's in biotechnology, it's probably, again, going to be more focused on the instrumentation and the equipment that's related. Biomedical science doesn't necessarily involve engineering. So that would be, what would distinguish that, like biomedical research or biomedical science could be, any sort of medical research lab or clinical research lab, that exists here at Hopkins, but not necessarily one using quantitative or engineering approaches. And biomedical engineering, being the third one, is what I always define it as, using quantitation and mathematical and analytical and design tools to engineer and manipulate biology. So that would be my answer there. Katie has a good question. What is the biggest misconception people have about bioengineering? I think, so to answer this question, I don't know what misconception or ideas people have sort of about bioengineering. But what I will say is a common misconception is, like, I'll introduce myself at, say, a wedding or, some sort of engagement event, with a bunch of people who haven't met me. And I'll say, yeah, I'm an assistant professor of biomedical engineering. Like, oh my God, you're so smart, right? Or, oh my God, you must be this total genius person, or whatever. And I'm not saying that biomedical engineers are idiots, or, that anything, to that sort. But I think there's this sort of impression that we're not human, right? That we're some sort of other species or otherworldly, whatever. And, we're up on some sort of pedestal or something like that. And at the end of the day, we're just real people who absolutely love and are passionate about biomedical engineering. And so I think the biggest misconception people often have is that, somehow being a scientist, being an engineer, being something like that, cuts you off from the rest of society, or means that you're, some sort of I think also people have this misconception of the mad scientists with their lab coat on, you know, with like little green potions, like, you know, going all over the place. And that's not what that is. Like, we're human beings like everyone else with real lives and real passions and interests in what we do. And yeah, I think people are often surprised that I'm as, quote, approachable as I am because of what I do. And I think that it's silly that people would even think that, you know, being in this career would affect, you know, my ability to relate or interact with anybody. So
Thank you for answering some questions. We actually have to end because the next speaker is going. Would you be willing to give us an email so that the people could ask like follow-up questions? Or
yeah, I think I got to most of them, but I see that a lot just came up in the last couple of minutes. So let me put in the chat my email address, which is just my name, Jamie.Spangler at jhu.edu, which is Johns Hopkins. And anybody who had additional questions, just shoot them my way, and I'm happy to respond that way. But yeah, I do have to actually go. It's yeah.
Thank you so much for coming and speaking with us. Your passion really shows like through your words, and we really appreciate you coming.
Thanks so much for having me. I'm glad that I got to chat with you guys, and hopefully to more people who will watch this recording. And you know, if you ever have any questions or anything specific about Johns Hopkins, please reach out to me.
Okay, thank you so much.
All right, bye.
Thanks, Dr. Spangler.